Okay, now recording. Trying to share the screen. All right, so we're down to our last sections, 2.7 and 2.8. Again, I'm going to treat it pretty much as one section. It's just one great big section, so I'll be jumping back and forth between them pretty much here. Okay. Now, yesterday I was focusing mostly on the derivative definition, limit h approaches 0, f of x plus h minus f of x all over h. If I have time, I'll do some more, but I want to focus on the graphical types of problems now. So the idea of the slope of a tangent, and also the concept that it's a velocity, right? So the derivative gives us the instantaneous rate of change or velocity also, okay? So yesterday I did a lot of limit h approaches 0, f of x plus h minus f of x all over h. Today we'll aim to do as many of the graphical types of problems as possible. So I'll be jumping back and forth. It seems like I'm all out of order, but there's a reason for that. I want to do a whole bunch of derivatives by the formula and then a whole bunch of derivatives by the graphs. And so that's why it's jumping back and forth like that. Okay, so I'm going to focus mostly on graphs now. So back to 2.7, start with problem number 11. Okay, a particle starts by moving to the right along a horizontal line. The graph of its position function is shown. When is the particle moving to the right, moving to the left, standing still? Draw a graph of the velocity function. Okay, so here's what's happening. This is distance away from home, so to speak. So when this experiment begins, you haven't gone anywhere. Makes sense. And after 1 second, 3 meters away. 2 seconds, still 3 meters away. 3 seconds, 1 meter away. 4 seconds, 1 meter away. 5 seconds, 2 meters away, and 6 seconds, 3 meters away. Okay. So that means the particle is moving to the right between 0 and 1. Correct? It goes from 0 to 3. It's also moving to the right from 4 to 6. It's basically whenever you have a positive slope. Okay, so the answer for when is the particle moving to the right, it would be 0, 1, union 4, 6. And maybe I'll write that here. Good, so 0, 1, union 4, 6 is the answer to this. Moving to the left. Well, right here, the distance away I am is 3. Here it's still 3. And now it goes back to 1. So that means whenever I have a negative slope. So moving to the left, where is a negative slope? Between 2 and 3. So 2, 3 for that part. And then standing still. Well, here we are 3 meters away. Here we're still 3 meters away. So it's standing still. Here we are 1 meter away. Here we're also 1 meter away, i.e. standing still, which means you have a horizontal line, right? Slope is 0. Okay, so standing still, I'll draw an arrow here. That would be from 0 to 1, union from here to here, 3 to 4. Okay, so moving to the right, standing still. Moving to the left, because you went from 0 to 3, you're still at 3, then you walk backwards to 1. That means you're moving to the left. Then you stand still, because you're still at a distance of 1, and then you go to 2, and then you go to 3. Right, so then again, you're moving to the right. Now, draw a graph of the velocity function. You're basically taking slopes. Okay, so this slope is 3 between 0 and 1. This slope is 0. This slope is negative 2 over 1 and down 2. Slope is 0. Slope is 1. Okay, I'm translating that into a chart now. And I'm not sure if I can show you both at the same time, but I'm going to give it a shot. Yeah, here we go. So you're coming with the slopes. Okay, velocity. Okay, so the slope is 3 between 0 and 1. And between 1 and 2, 0. Between 2 and 3, negative 2. Between 3 and 4, 0. And between 4 and 6, the slope is 1. Okay, and velocity should be meters per second. Sorry, meters per second. And now draw a graph of the velocity function. So I take these and put it to a graph. So between 0 and 1, velocity is constantly 3. Between 1 and 2, 0. Between 2 and 3, down at -2. Between 3 and 4, 0. And between 4 and 6, 1. Okay, so this is the graph of the velocity function, time versus velocity. And notice these are all open circles. Right at these endpoints, you don't have any velocity, okay, because there's a change, okay? Or you can say the limit from the left for the slope is 3, the limit from the right is 0, so I do not have a two-sided limit, okay? Likewise, whenever you turn, okay, this is going to be sometimes be called a corner point. We'll talk more about corner points. Okay, so corner point. The derivative doesn't exist at a corner point, okay? And there's a bunch of other corner points, that one, and that one. There's no one number I can say is the slope. Now, if I'm in the middle here somewhere, I know what the slope is, it's -2. Right here though, I can't say the slope is -2 because if I'm coming from the left, the slope is -2, but if I'm coming from the right, the slope is 0. So again, I don't have a two-sided slope, so to speak. So that's what we have for that one. Okay. Okay, and yes, so these have to be with parentheses, not brackets, if you're listing these, because we're not including the endpoints. A question about brackets or parentheses. Okay, so yes, the slope or derivative or velocity does not exist right at 1, 2, 3, 4, or 6. So they're all parentheses in this case. Okay. All right, next one I want to show you is 17. Arrange the following numbers in increasing order and explain your reasoning. Okay, we're not going to explain the reasoning, we're just going to do it. Okay, so please notice when it says G prime, we're looking for slope. If it just says G, you know you're looking for the Y coordinate. So G of 0, G of 2, G of 4, you're asking for the height. Not here, now you're asking for the slope. Okay, so G prime of -2 means what's the slope right here. G prime of 0, you want the slope right there. And G prime of 2, you want the slope right there. And G prime of 4, you want the slope right here, and so on. Okay. All right, so let's look. You just have the number 0. G prime of -2. Okay, that looks like a fairly steep positive number. Imagine it's a ride, a roller coaster ride. And a roller coaster ride, you're always going from left to right. You're going this way. So here you would say steep positive. Okay, and then at 0, you're going down, right? You're going down the roller coaster. Then at 2, you're going back up, but it looks like it's not as steep as this one. And then G prime of 4, you're still going up, but you're kind of leveling off. Okay, so you want to think of imagining a little tangent line here and here and here and here, right? So put them in increasing order. Well, there's only one that's negative right here, so it's G prime of 0. And then the number 0. This is negative, that's 0. So for 17, G prime of 0 first, and then 0. All the others are positive slopes, aren't they? G prime of -2, slope there. Again, it's not the Y coordinate, it's a slope. And G prime of 2 and G prime of 4. So if you're on this ride, if you're on this roller coaster, here, here, and here, in each case, you would say, oh yeah, I'm going up. Okay. Let's get them in order of steepness. This to me looks like it's the least steep, right? It's leveling off. And then the next steep is that one, and then that one. So that's why I have this order now. So I can't move it over much without the book falling off my table. But G prime of 0, it's the only one that's negative. And then the number 0, okay, this is negative, positive, 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 right? G prime of 4 is positive, but not as steep as G prime of 2. And then this one looks like it's the steepest. right? If I'm on this roller coaster ride, you're kind of going up like that, right? And here you're leveling off. So this is the answer in order of increasing number. Negative, the number 0, and then 3 positives. This looks to be the least positive. It's not as steep. G prime of 4. G prime of 2 is steeper, and G prime of negative 2 is the steepest. Okay. All right, so that's how you do that one. Okay, 21. 21, if the equation of the tangent line to the curve at the point where a equals 2 is 4x minus 5, find f of 2 and f prime of 2. So this one's a little bit different. They don't give you the function. They do tell you the tangent line. So how do I find f of 2? I plug in 2. 4 times 2 minus 5. F of 2 is 4 times 2 minus 5, which is 3. Okay. Now, agreed, they don't tell us what the function is. They tell us the tangent line, but the function and the tangent line have to agree at the point of tangency. So I'm allowed to just plug into the line. So that answer is 3. Okay. And then the second part, f prime of 2. That tells me the slope. Well, what's the slope of this line? mx plus b, 4. Okay. So here's the answer to 21. F prime of 2 is 4. Slope is 4. So f of 2 is, just plug it in, 4 times 2 minus 5 is 3. F prime of 2 is 4. Okay, and that would be my slope. Okay. Okay, I know I'm kind of digressing now, but I have it on my paper, so I might as well give it to you. There is one derivative in 2.8 that I alluded to, so I might as well give it to you, the setup for that. Problem 31 in 2.8 asks for the derivative of x to the 4th. Okay, and I alluded to this earlier, so let me go ahead and address that. This is for 2.831. So I'm not really answering the question, but I'm just giving you a heads up for that. Okay, so let me go ahead and show it to you. X plus h to the 4th. How do I get x plus h to the 4th? One way you can do it is to go x plus h squared, which is x squared plus 2x h plus h squared times itself, and then multiply all that stuff out, right? Okay, x squared times that, 2xh times that, and h squared times that. Okay. Another way is by doing something called Pascal's triangle. Okay, and here is Pascal's triangle. It goes down infinitely far. Okay, now you say, what is Pascal's triangle? So Pascal's triangle starts off with a 1, and then the next row you go 1, 1. So all the outsides you put 1, and then the inside stuff you add the 2 numbers that are just above it. And I've indicated that with little lines there. In other words, 1 plus 1 is 2. So 1, 2, 1. Next level, put a 1 and a 1, and then add 1 plus 2 is 3, 2 plus 1 is 3. Then the next level, which is what I want, 1, 1. Then you go 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. 1, 4, 6, 4, 1. Okay, so to do a plus b to the 4th power, the coefficients are 1, 4, 6, 4, 1. Okay, then the first letter a, you start at the highest exponent and go down. You go a to the 4th, a cubed, a squared, a to the 1, and a to the 0. The second variable goes the opposite, b to the 0, 1, 2, 3, 4. Okay, so that's how you do a plus b to the 4th, or x plus h to the 4th, same thing. For 1, 3, 3, 1, that's the coefficients of a plus b cubed. So for a plus b cubed, you would go a cubed, a squared, a, and then a to the 0, which means you don't write it. And then b to the 0, which means you don't write it. B to the 1, 2, 3. And the coefficients are 1, 3, 3, 1. Okay, so that would be a cubed plus 3 a squared b plus 3 ab squared plus b cubed. You don't have to write that down if you don't want to. This one you should know, 1, 2, 1. A squared plus 2ab plus b squared, right? So it goes a squared, 2ab means there's an a, and then the last one doesn't have any a. And b goes backwards, right? A squared, b to the 0. then 2ab, that means b to the 1, and then b squared. Okay, so use that to help you with problem 31 and 2.8. Okay. Okay, continuing on with some of these. Okay, 23. Sketch the graph of a function with the following properties. F of 0 equals 0. Okay, that means it goes through the origin. And the rest all talk about f prime. F prime means slope. So slope at the origin is 3. Slope at 1 is 0. Slope at 2 is -1. Notice they don't give me any of the y coordinates. So you can let the y coordinates be anything you want. Okay, and just curve it appropriately. Okay, so here's what I have for 23. F of 0 is 0. We got that. Okay. And then after that, slopes. So slope at the origin is 3. So I just kind of aim it like that. Okay. Slope is 3. So how do you know it's, well, you guesstimate over 1 and up 3, only just drawing a tiny little piece with a slope of 3. Doesn't have to be that accurate, but it's going up like so. Okay. And then the slope at x equals 1 is 0. Now you say, where's the y coordinate? I don't know. It can be anywhere. It's got to be higher, of course. So right here, slope is 0. So horizontal tangent. And by the time we reach x equals 2, slope is -1. -1 means falling at a 45-degree angle. Okay, so here's an example of a possible graph for number 23. Okay. All right, so again, the only point they give me is the origin. Then slope is 3, slope is 0, slope is -1. Yeah, the graph could be way up here or down here, as long as you have the slope considerations that they're asking for right there. Okay. So that's how that works. All right, thank you, Prasanna. So those of you who look at the chat, Prasanna is going to have something in the email if you want to review with him. So thank you, Prasanna, for that in preparation for the test. Okay, so I'll give you that one. 25. Watch out here. Sketch the graph of a function that's continuous on its domain, -5, 5. Notice it's parentheses, meaning don't include -5, don't include 5. G of 0 is 1. That's a dot. Slope at 0 is 1. Okay, so when it says G prime, it means slope. Slope at -2 is 0. Limit as x approaches -5 from the right is infinity. Limit as x approaches 5 from the left at G of x is equal to 3. Okay, so let's see what we got here. So let me try to show you a sample graph. I'll raise it up for those of you who don't have the book. If you have the book, of course, just look in your book. So only define from -5 to 5. So my graph only goes from -5 to 5, not counting -5 and not counting 5. Okay, then let's see, what else does it say? G of 0 is 1. Okay, touches 0, 1. Now we have some slopes. G prime of 0 is 1. So the slope here is 1. Slope of 1 means going up at a 45-degree angle. Slope of -1, falling at a 45-degree angle. G prime of -2 is 0. So I know it has to be lower. So where's the y coordinate? We don't know. So I just decided to put it on the x-axis to make it easier for myself. So slope is 0. So it works. There's actually infinitely many solutions for these kind of problems sometimes. Okay, then it gives us a couple of limits. So limit as x approaches -5 from the right of the function is infinity. So I come from the right, it shoots up to infinity. And then it says limit as x approaches 5 coming from the left of the function is 3. So 1, 2, 3. So if I come this way, I get real close to 3, but it's got to be an open circle because the domain said parentheses -5, 5. So don't count -5, don't count 5. So here's a sample graph of what would work here. Okay. Right, so that's how those work. And now let's see. I'm definitely jumping around in order to do what I need to do. Okay, go to 2.8, which has more of these kinds of things. 2.8. Yeah, show you some of these. Trace or copy the graph of the given function, then use the method to sketch f prime below it. Okay, I want to go to number 9 because they're all linear. Okay, so this thing that kind of looks like a W. Okay, so let's look at number 9. Goes like this. Okay, so I'm trying to graph the slopes. So this looks to me like a slope of about -0.5. So how do you know? I don't know. Okay, I know if it falls like this one at a 45-degree angle, that's a slope of -1. That's a slope of 1. Okay, so that looks like a slope of 1. Slope is -1. That looks a little bit less steep than -1. So I said -0.5. And that one I called +0.5 in terms of steepness. Okay, so one more time. If a line goes up with a slope of 1, it's going up at a 45-degree angle. That looks like -1. So that's what I got. Slope is 1, -1. And I said that's -0.5, +0.5. Okay, so now they want the graph of x versus f prime versus slope. Okay, slope is undefined here at a corner point, corner point, corner point. Okay, derivative is undefined. Okay, so right here, and these x coordinates are supposed to line up. So in other words, this is supposed to line up with that lines it with that's 0, that lines it with that lines it with that. Okay, so right here, slope is -0.5, +1, -1, +0.5. Okay, so here's a sample of what you would have for 2.8, number 9. Okay, these are constant slopes. Okay, constant slope, constant slope, constant slope, constant slope. I want to start off with the easier one with a constant slope because for some of the graphs after a while, they're not constant. They're going to keep moving. They're going to change. Okay, so I'll show you how that would work. Okay, so one more time, -0.5, roughly there, +1, -1, +0.5. Okay. And yes, you are allowed to put some of this stuff on your cheat sheet if you wish. Remember, for the test on Friday, you're allowed to have one formula sheet, put anything you want, any formulas, any sample problems on one sheet of paper, 8.5 by 11, front and back, both sides, for the test on Friday. Okay. All right, so that's that one. Okay, now I'm going to go back to 2.81 because here the slopes are not constant. 2.8, number 1. Use a given graph to estimate the value of each derivative, then sketch the graph of f prime. Okay, so there's no straight lines here. Everything is curved. Okay, so I came up with my little table, I suppose. Okay, so f prime at nice integers, -3, -2, -1, 0, 1, 2, 3. Okay, so at -3, you want the slope. You're on this roller coaster. Pretend you're on a roller coaster ride. Okay, so if you're right there, you would say that you're going down, right? Going down a little, but not very steep. I called it -1/3. Okay. What seems to be the slope right there? 0, leveling out. And right there, I would say 1. Right there, the tangent line, okay, on the roller coaster ride, you're going like that. Looks like you're going up at about 45-degree angle. Here it looks steeper. Okay, so if I went in a straight line, it looks like it's going to aim right over there. So I would say that's about 2. You're going up the ride, correct? You're going up the roller coaster. How about right there? What seems to be the slope of the tangent line? Again, I'd say it's about 1, 45-degree angle. And what's the slope right there? Looks like 0. And right here, again, you're going down only a little bit, -1/3. Okay, so let me show you the table that I came up with. And it's hard for me to show you both the table and the graph at the same time the way I am. So let me just show you this. So if you want to catch this, you may, or catch the video later also. So -3, -2, -1, 0, 1, 2, 3. I just tabled everything that I said here. Let's see if I can push the book higher. No, I can't because it's going to run into my computer a little bit. Okay, so I'm going to try to show you that. I know it's blurry. Okay, so at -3, I'm going down a little bit. I called it -1/3. X equals -2, slope is 0. Notice it's a completely different game. We're used to saying, give me an X, I'll come back with a Y. We can still do that. But now the game is, give me an X, come back with a slope. Okay, at -2, the slope is 0. -1, the slope is 1. If you're on this ride, how steep is the ride, so to speak? Okay, 1. And then I said 2, steeper. Notice I'm not interested in the Y coordinate. I'm looking at the slope. Okay, and then X equals 1, slope is 1. Then at the top, 2, slope is 0. And then at 3, again, I'm going down a little bit, right? If you were on this roller coaster ride right there, you would say, okay, I'm going down, but it's not very steep. So I said -1/3. Okay, now, after that, graph F prime. So I just make the usual graph of X, except of having Y coordinates, the heights are F prime. Okay, so here that goes. So this is different. It's not X versus Y, it's X versus slope, X versus F prime. So what did I plot? -3, -1/3, there it is. -2, 0, -1, 1, 0, 2, 1, 1, 2, 0, 3, -1/3, and I connect them, and it looks something like that. So this is a graph of the derivative function. The derivative function looks something like that. Okay, so again, here's the table that I came up with, and here's the graph. Okay. All right, I'm going to now jump to 41 to 44 of section 8. Okay, and yeah, sorry, I know I'm bouncing around, but again, the author, Mr. Stewart, jumps between the limit definition and graphs and so on. So I want to do, I want to do a whole bunch of derivatives yesterday, and today do a whole bunch of graphs. Okay, so the last functions, 41 to 44 on 163. State with regions the numbers of which F is not differentiable. Okay, fancy word, differentiable. Okay, that means you can take a derivative. Okay, so a little bit of language here. So if you can take a derivative, the function is called differentiable. Okay, and one other thing, page 155. Okay, notation for derivative. So notation. The big three are these: F prime of X, Y prime, dy dx. It looks like dy over dx. Okay, but we're just going to say dy dx. Dy dx. Okay, these are the ones we're primarily going to use. We are hardly ever going to use any of these other ones. Okay, but that's enough. So F prime of X, Y prime, dy dx. The D notation is sometimes called the Leibniz notation. Leibniz notation. Okay. It does tell you what the variables are. The variables are Y and X, which these don't have. Okay. Now, at first glance, you might say this is the clumsiest, and I would agree, the most amount of writing compared to these. But later on in chapter 3, we're going to see that there's a very good reason for having this notation. In fact, some problems are much easier when you have the dy dx notation. Okay, so it looks like dy over dx. In some sense, it's kind of like delta y over delta x, right? Now, delta y over delta x is for slope. This is dy dx in the limit. Okay, or you can think of dy and dx are very, 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 very tiny changes of y and x. So it looks like dy over dx. We're going to call it dy dx. And don't try to cancel that out. This is one symbol. So for instance, you might say, oh, can I cancel the d's like in algebra? No. Okay, this is all one symbol, dy over dx, but we say dy dx. Okay, so language. Okay, the process of taking a derivative is called differentiation. Okay, yes, there's an English word differentiation. Okay, but in calculus, when we say differentiate, it means to take a derivative. Okay, so you have to be careful now when we say differentiate something. If you're just speaking in a regular English context, differentiate, right, to distinguish between one thing and another. In calculus, differentiation means take a derivative. Okay, if you can take a derivative, the function is called differentiable. So you can have differentiable or non-differentiable. Okay, so I guess this would be the adjective form, right? Adjective form, a differentiable function, I can take a derivative. Okay, so you will hear differentiation, differentiate. The verb form differentiate means to take a derivative. That means technically you're not supposed to say derive a function because derive has another meaning. Okay, you differentiate a function. So differentiate a function means to take a derivative. Okay, so differentiable, okay, and so forth. Okay. Our author even says Leibniz notation right there. There we are. dy dx, so-called Leibniz notation. Okay, so how can a function not be differentiable? Page 157. How can a function fail to be differentiable? Okay, if you have a corner point, okay, if you can see in the book there, it says a corner or a kink to it. There's no one tangent you can have. So if you look at the absolute value function, y equals absolute value of x, right there, you don't have a derivative. Okay, there's no one number you can call the slope, because if you come from this side, you would say the slope is -1. If you come on this side, the slope is 1. So I don't have any one number as a slope. Unlike over here, it doesn't matter if I'm coming from the left or the right, the slope is 1, right? Same thing over here. So if there's a corner point or a kink to it, okay, then it's going to be differentiable. Okay, if a function is not continuous, then obviously it's not differentiable either. Okay, so figure 7, page 158. How can a function fail to be differentiable? Okay, corner point. Discontinuity, it's not continuous. So if it's not continuous, it's automatically not differentiable. Okay, now C, you actually have a tangent. It's a vertical tangent, but it's straight up and down. And what's the slope of a vertical line? Slope of a vertical line is undefined. So there is a tangent, it's smooth, okay, but there's no one number you can call as the derivative as the slope. So that's why in this case, we would say the function is not differentiable, even though there is a tangent line. Okay, I guess one way you can think of it, if you're into roller coasters again, is, you know, except for C is okay, but if you were actually thinking about roller coaster rides, these are, you know, dangerous points on a roller coaster. I mean, if you look at a roller coaster that looks like that, something tells you, you know, that isn't right. I'm not going to get on that roller coaster. Okay, and I'm definitely not getting on that, right? You're just going off here, you're falling down here, right? That doesn't seem right. Okay, so this is a quote unquote dangerous point on a roller coaster. That doesn't seem right. Okay, so if you look at, you know, roller coasters, you know, they can do all kinds of stuff upside down, loop to loop and whatever, but it's all smooth, continuous and differentiable. You can draw a tangent line. Okay, you never see that. You definitely don't see that, at least not now, unless they make up something which flies down or something like that. This would actually be okay. I've seen that. Okay, you have a vertical tangent. Okay, so it kind of goes down, you're heading straight down, and then of course you can't keep going like that, then the track would start turning off somewhere else. Okay, but one way to think of non-differentiable in these two cases is it's a dangerous point for a roller coaster. You never see roller coaster rides like that or like that in general, right? Okay. All right, so let's knock off 41 to 44 quickly. So where is the function not differentiable? Now, please notice differentiable is different than continuous. Okay, so for instance, right here, the function's still continuous. I can draw it without lifting up my pencil from the paper, but it's not differentiable. I don't have one tangent line. Okay, okay. This does not look like a feasible roller coaster ride to me, right? To go like that. Okay, so where's the function not differentiable? Here I would say -4 and 0. Okay, so, and here are the reasons for 41. So 41, -4 is a corner point, and 0, the function is discontinuous. 41, -4, corner point, and 0, discontinuous. Everywhere else, the function is differentiable. Okay, so differentiable here, right? I don't mind being on a roller coaster right here. Smooth, there's a tangent. Okay, right here, tangent, tangent, everything seems fine there. Okay, 42. So what's wrong with 42? Discontinuous and a corner point, right? So for 42, see if we can get that right there. At -1, the function is discontinuous, right? You have to stop and draw that dot up there and come back. And then at 2, you have a corner point. Everywhere else, the function is differentiable. Okay, differential, smooth. Okay, I don't mind being on a roller coaster ride here or here or here. Okay, but right here, it's a corner point. It's still continuous, but there's an abrupt change in direction. So one way you can define a corner is an abrupt change. You quickly, jet out in another direction. So you take a corner, like the corner of a room, the corner of your room, right? It starts like this, and then there's an abrupt change, a quick change in another direction. Okay, so this is smooth. I'm okay on a roller coaster here. That doesn't look right to me, right? The roller coaster doesn't seem like proper. Okay, but here it looks smooth, right? It's going like this and so on. Okay, and how about 43? They didn't draw it very well, I suppose, but let's assume right here there's a vertical tangent. Okay, at 5, vertical tangent, which means not differentiable and not continuous there. Okay, so 43 at x equals 1, discontinuous, and at x equals 5, vertical tangent. It may not look quite vertical there, but I'm going to assume Mr. Stewart wanted that to be vertical tangent. If it wasn't a vertical tangent, then it would still be differentiable. Pretty big slope. And finally, 44. Okay, where's the function not differentiable? Corner point, discontinuous, corner point. Right? They don't make roller coaster rides like that, right? Or like that. That just doesn't look right. That looks okay. That does not look okay. That's okay. And going straight, that seems okay. Right? So for 44, -2, x coordinates, -2 is a corner point, x equals 1, discontinuous, and x equals 3 is a corner point also. Okay, so that takes care of that. Okay, what time is it? Yeah, I'm probably not going to have an in-class assignment at all today or tomorrow or any of this week. I want to make sure that I can finish everything so I can possibly give you questions and answers. And so, like I said, it's nice to have the 2 holidays, Friday and Monday, but the bad part is I lost those 2 days, so I have to make up all that. Whereas if I taught this class last semester, we didn't have those holidays, but it means I had more time to spread everything out. So we had the 2, not that I'm complaining, I like the holidays too, but it just means I have to, finish everything quicker before the test on Friday, okay? All right, now some more of these kind of graphs. So back to 2.8. Stuff like number 7. Okay, trace or copy the graph of the given function and then try to graph f prime below that. Okay, so I did number 9, where you all have constant slopes. We said what? That was -0.5, +1, -1, +0.5, something like that. Okay, 7's a little bit harder. It's a semicircle. Okay, so what do I do there? So here's my semicircle, and here's y prime, or the slope below that. Okay, and technically these line up. So that x lines up with that, That's still 0. That lines up with that. Okay. So if I'm right here just a little bit to the right, it's a big positive, right? If I'm on this ride, on this roller coaster, right here, I'm practically vertical, correct? Big positive. And what does it say up here? Small positive. Okay, I'm getting near the top of the ride. Okay, I'm still going up, very small positive. And what's the slope at the top? 0. And then I have a small negative. And by the time I get to here, you're almost going like that. It's a large negative. All right, here we go. Big positive, small positive, 0, small negative, large negative. So it's going down something like that. You can say that the slope is always decreasing. Okay, big positive, 1,000,000. Drops down to 1, then 0. 1,000,000, 1, 0. Small negative, like -1, and then a large negative. So there we go. Okay, so that's how you do that kind of problem. Okay, and then 11. Okay, going like this. Okay, and what do you notice right here? Vertical tangent. That means the function should not be differentiable here. I don't have a derivative here. Still smooth. Something about this ride. Pretend you're on this roller coaster ride. Again, you're always going this way. For this ride, you are always going which way? You're always going up, aren't you? Okay, so here I'm on the roller coaster ride, right? Going like this. You'll hear me reference roller coasters a lot in this class. You know that's how you can think of it as a ride. So you're going like this. Then right here, you're kind of going straight up, right? And then it levels off. So it's always positive. Let's see, small positive, then shoots up toward infinity. Big positive, small positive. So here we go. The slope is always positive. That means on this graph, x versus slope, I'm always above the x-axis. So there's no graph down here. Okay, I can't have anything here because down here, that means the slope would be negative, but I'm never doing a negative slope here, right? For this particular roller coaster, I'm always going like this. I'm never going like that, correct? So it goes from small positive, shooting up toward infinity, then right at 0, undefined. Then I move a little bit to the right, big positive, small positive. So it looks like so. Okay, that's the way that works. All right, let's see, what time is it? I just have time to do that one derivative that I was talking about, 2.831. So going back to the limit definition of a derivative, I'll do more of these, hopefully tomorrow or Thursday. Okay, find the derivative of x to the 4th, number 31. Okay, so let me do this, and then that's probably all the time we have. Okay, it's 2.831. F of x is x to the 4th. Okay, again, those of you who know the shortcut, don't use it. If you do the shortcut, you're going to get a 0. Okay, and others of you saying, what shortcut? Don't worry, hang in there. We'll give you all the shortcuts you want, chapter 3. Okay, so right now, pretend there's no shortcut. All right, so f prime of x is limit h approaches 0 of f of x plus h to the 4th power minus x to the 4th all over h. Okay, so limit h approaches 0. So we already talked about this. The coefficients are 1, 4, 6, 4, 1. You can either multiply that out or use Pascal's triangle. Remember I showed you Pascal's triangle, right? 1, 4, 6, 4, 1. It goes x to the 4th, 3rd, squared, 1, and 0. H goes the other way, H to the 0, 1, 2, 3, 4. So all of this is x plus h to the fourth minus x to the fourth, all divided by h. X to the fourth cancels out. So that one, that one, that one, and that one all have a common factor of, guess what? H. Factor out the h, parentheses, 4x cubed plus 6x squared h plus 4x h squared plus h cubed. Let me raise it up for you. There. Cancel the h's, cancel the h. Keep writing limit. I'll see if you write it. So even if you get the answer correct, so-called, if you write it incorrectly, I'm allowed to take off points. It's important that you write mathematics properly. So limit h approaches 0, lim h approaches 0. Keep writing lim until you're ready to plug in. Okay, so now I have limit h approaches 0, 4x cubed plus 6x squared h plus 4x h squared plus h cubed, because the h's cancel out. Now I plug in h is 0, which means that's gone, that's gone, that's gone. And by the way, if I give this to you in a test, you don't have to actually draw that. I'll let you, but you don't have to. So that's nothing, that's nothing, that's nothing. So you have 4x cubed plus nothing plus nothing. Final answer is 4x cubed. So the derivative of x to the fourth is 4x cubed. And now, yes, those of you who know the shortcut, you can use that sort of as a double check, but you can't use that as your primary source of doing this problem. You have to show me all this stuff here, okay? All right, so that was my goal today, was to mostly focus on graphs, and tomorrow I'll try to tie everything in, get all the leftover graphs and derivatives by using the definition as possible, okay? All right, that'll do it for today, folks. So we're just about out of time. Okay, so we'll see everybody tomorrow. All right, have a good day. See everybody. Bye.
All right, see ya.
Bye, Professor. See you tomorrow.
Okay, Prasad, thanks. Bye.